plan for today. So last lecture, we said what is NP-complete problem, and we can prove that some problem is NP-complete by taking a known NP-complete problem and reduce to our new problem. And then our new problem, we understand also. I will repeat this in detail just in a second. And so we will prove that all the problems you see on the board are NP-complete. This is the plan. We will not manage to do all of them, but at least half of them should be possible. We will see how far we get. The other ones I will write in the notes, hopefully soon. When I have time, I will write the proofs. But I mean, it just, here are important problems, and in the seminar are more important problems. And you can use all these problems to prove NP hardness. And then for those who are curious, I will write the missing reductions in the notes. Okay. Okay. And the seminar we are allowed to use only. Yeah, all of this tree you can use. But nothing problems. Well, you can, if you are free to use any problem, you can say, okay, I define this problem as one I'm allowed to use. So, no, yeah, I mean, it is common known complete problem, but it's not in this tree. Can we use it? So which one do you want to use? One more question. Can we use some theories from fixed books at our home classes? Yes, so, yeah. You can use everything from Sipser book. Well, okay, I need to be careful. Yeah. So it's my task to check that the answer is not a theorem in Sipser book. Okay. So I explained the plan, and so let us quickly repeat what we said last lecture. So what is reduction? So reduction from A. So we have this notion A polytime reduces to B. So A is a language, a subset of string, blah, blah. A reduces to B. If there exists a function that maps inputs of problem A to inputs of problem B. And there are two conditions. So first condition, you remember, you need to count the function in time. Yeah. Well, it is R or B. Yeah. I can't say what is the answer. X can be computed in time poly length of X. So we will always speak about graphs and matrices, but you know that it translates to languages under the hood, and these inputs have a certain length, can be computed in time poly length of X. And second condition, X in first language, yeah, X and B. So that's actually two conditions. So 1, 2, 3, we have to prove this inclusion and this inclusion. And 99% of cases, it's better to use positive information here, get positive here, and vice versa. Okay, you will see an examples. So this is a reduction. And then there were some properties of reductions. What do you remember? Which properties? So let me write. There's a bit of here on the bottom. The properties of NP-complete and NP-complete languages. For example, if A is polynomially reducible to B, and B is in P, then A is in P. This is one. Then we had a definition. Also transitivity, A reduces to B, B reduces to C. Yeah, A reduces to C. We had the definition of NP hard. So A is NP hard. Sorry, let's say B is NP hard. if for every A and P, A qualifying reduces to and B is NP complete. Yeah. So these are the definitions. So B is NP complete if from every problem, so here problem 3 set is NP complete if from every problem of NP we can reduce to 3 set. And so next lecture I will give you like a generic reduction where you can plug in any problem from NP. But for now we will get used to reductions by going from 3. So and this will imply that 3 set is NP hard. It's also in NP. You remember what is this problem 3 set? Yes. Okay, let's. I will write it in a minute.
It seems like reflexivity is also a property of the reduction.
Yeah.
But what about it?
Can we close the because I'm a bit sensitive. So NP yeah. So it means that after we prove 3 set is NP complete, then we prove a reduction, for example, from 3 set to independent set problem. We conclude that independent set problem is NP complete because from every problem in NP we go to 3 set. From 3 set we go here. So from every problem here we can go to independent set by transitivity. So that's so after we believe this, we will prove that all these problems are NP complete. All these problems they are in NP themselves. So and this is interesting because NP complete problems are in some sense the same. So when we prove a reduction, we're basically saying that A is a special case of B. So if we can prove if one day a person finds polynomial time algorithm for the problem B, then we just need to decide A. We just need to solve B even on special cases. And so that means if a person, if there is just a single problem that can be solved in B from all the NP complete problems, it means that all problems in NP can be solved in polynomial time.
Well, but it is also true for X and other complexity classes, yes?
Yeah. It's one problem in X.
The main idea of construction.
Yeah. Okay. So we already know that X is not equal to P. So it will not happen for X, but maybe for P space, it can happen.
For this graph, we don't know how the clique problem will solve the DOM set, for example, problem, because it's like they don't have a relation, they have common.
Yeah, but clique is also in NP.
Yes.
So if somebody solves clique in polynomial time, we know it's an NP and we can go to dominating set. So, okay, if we believe in this reduction, I will not tell today, but after next week, or maybe 2 weeks. It's the end of next week or beginning of 2. Okay, that doesn't matter. After we understand this link.
But in reduction, maybe I'm forgetting something. When you, in this definition, when you solve A, you don't solve B. You solve B because you can just.
Yeah, if we can solve B, we can solve A.
And
that's what we say.
And if we can solve A, can we solve B?
Yeah, so if we can solve B, then we can solve A. If so if B is that's for
it's the opposite rule. If we can solve A, can we solve B?
Well, in the special case that B is NP complete, the answer is yes.
In general, it's not true.
Okay. Sorry, in case if A is NP complete, then the answer is yes.
But the whole point is if you can solve the more complex problem like B, you can you have reduction from A to B, then you can solve A if you are able to solve B.
Yes, but if we prove only what's written in this graph, on this, we can be sure that
Yeah, but
P is NP-complete.
like contains also everything here.
Yes.
No, you know that click is NP, and you know that every NP problem is reducible to click, because every NP problem is reducible to trisat, and trisat is reducible to click. And using transitivity, you know that every NP problem is reducible to click, and then click is NP hard.
Okay. Okay. Okay.
Yeah. So from every problem here, we are go here. Okay. And so why is it useful in software company? So your boss tells you make polynomial time algorithm for dominating set or whatever. It will be hidden under some technical things. And then so you don't know about NP completeness, and then you tell your boss, sorry, I cannot invent it. It's too difficult. And then your boss thinks, maybe he's stupid. But if you tell him, look, it's NP hard, then he understands all it's NP complete. All NP complete problems is actually the same problem because they reduce to each other. And decades, best mathematicians, they're really clever people, best mathematicians been thinking about cracking this problem, they failed to do it. And so you can say, okay, I failed to do it, but it doesn't prove that I'm stupid. It proves only that I'm more stupid than all these huge, clever mathematicians who dedicated their life during decades. Only so then the boss will say, okay, I will not fire you. Let's go for heuristics to go around NP hardness. Let's change the problem. Let's find assumption. Maybe if he has money for computing power, let's do some brute force search. And so on. So all things that we will, like parameterized complexity is one approach, approximation, and so on. So you have different discussion. So that's why we need NP completeness. But okay, as I already told, we need to be careful, because by the time you are senior enough to have such discussions, you already forgot what is in this course. But maybe you can learn it faster if you learned it when you were young. Like people who learn piano when they're young, they can learn it again when they're old. And so, okay. But okay, let's be positive. At least the project I'm doing is, it's like half of the meeting. We say, oh no, we cannot go there. It's NP hard, and then we cannot go there. Important also is strongly NP complete and weakly, and strongly NP hard and weakly NP hard. I will tell it in the end of the lecture what it means. Okay. So this is enough blah blah again. Let us now go to the arrows. So we already did a few ones, like from independent set problem to click problem. We explained last lecture. It was an example. So let's now look from tree set problem to independent set problem. And so let us recall what is tree set problem. So in the input is Boolean formula in 3CNF. So what means Boolean formula means you use and, not, and or operations. 3CNF is you have an and, of, ors. So example of formula in 3CNF is x or y, and x or not z, and x or y or something like this. Is an example of formula in CNF. Formula in 3CNF, it means that every clause has length at most 3. What is a clause? It is just a part, so an or sequence. So this is clause. Clause, so 3CNF means every clause has at most 3 literals, where in general KCNF at most k literals per clause. So this is formula in 3CNF. and Boolean satisfy. So the three sat problem, there the input is Boolean formula. So formula in 3 CNF. And the question is, can you assign to the variables values of 0 and 1 so that the formula equals to 1? So that means every clause contains a true literal. And 3 C and F. Let's say formula phi. And the question exists 0, 1, n. Let's say n is the number of variables, so we need n bits such that phi of x is equal to 1. So that's a 3-set problem. And so let us reduce it to the independent set problem. So here we get a graph. So input is a graph and an integer k. Let's write graphs as pairs, a set of vertices and an integer k. Exists a set S, size is equal to k. The set of vertices so that every pair of vertices is disconnected. And so pairwise disconnected. So this is independent set problem. Yeah. We speak about the we spoke about it. It's a simplification, but it's if we don't care about polynomial time, it is equivalent. So that was first lecture.
Well, you want to say that there was existing dependent set of size k, the formula is satisfied.
Yeah.
And,
so let's make a small illustration of independent set problem for those who are new. Okay, so this graph, does it have independent set of size 2? Yes. It's independent set of size 3. It's no, okay. That everything is clear. And so now we want to transform formula to independent set. So now we will want to build a reduction. So here A is 3 set, B is independent set. So how can we transform it? So let us start with an example. I will use different example. Let's say X or not Y. And why not? Let's use the same example. Okay. So let us build the graph. And the graph will have a click for every clause. I will use this example. So I will map this. So I will go from top to the bottom. So here I will write here I will draw the graph. So we will go from here to here. So for every clause, we will have a click. And the size of the click is number of literals in the clause. So we have 2 clicks of size 2 and 1 of size 3. So click of size 3 is a triangle. I should be left here. And let us write labels according to the values. X not Z, and then not X, not Y, not Z. Okay. And then I will draw an edge between opposite literals. So for example, okay, let's remove this from the Z. So here we have not Z, here we have Z. So I will draw an edge here. We have X and not X, so here is an edge, not Y and Y. Here also an edge. And then finally, to finish the reduction, so know that the input of independent set is a graph and an integer k. K will be number of clauses. So that's here. This pair is the input. So I applied the reduction. We have to map a formula in 3CNF to a graph and an integer. Integer will be number of clauses. And so this is the function, and we have to check conditions. First, can I construct this graph and this integer and polynomial time in the input length of this formula? And so it's clear why, because number of nodes of the graph is number of literals, number of edges is at most number of nodes squared. So so the time to do this, say, at most cubic time in the input length, in the length of the clause. Okay. So one is okay. Now we have to check equivalence. So if the answer for the first problem is yes, is the answer yes for the second problem? So here, if we have an assignment, can we get an independent set? So here, what might be an assignment? For example, we can have x equals 1, y equals 0, and z already doesn't matter. Let's say 0 for z. Okay, and then we know that in every clause there is a true literal. We will select the true literal in every clause. So x is equal to 1. Let's use another copy. So now let's build an independent set of size 3, number of clauses. So from every click, I will select the true literal.
Why are you sure that in every clause we have a true literal? Because it is definable.
Yeah, so we assume that the answer here is yes.
Oh, okay.
And I've even drawn an example. If we choose x1, y0, and z0, then every clause has a true literal, and we can select this. Now, can you verify that this is an independent set, the 3 red nodes? Indeed. So there are no connections pairwise. And this will always work. If the formula is true, we can always get such an independent set, because in every click, we select the node with label equal to the true literal. So that's a construction. So for every clause, we make a click, and we label its nodes by the literals of the clause. So if the assignment is true, we select these literals and recall. So what are the interconnections between the clicks? Each time a node is labeled by a literal, we connect it to all nodes labeled by opposite literal. And then we will never have trouble. Okay, so edges of clicks are not dangerous because we select one. So the black edge is okay because we select one node in each click.
Why do we select only one node in each click?
Well, we have no much choice because if we select 2, then a black edge will kill us. And blue edges will not bother us because we can never have that the literal x is true and not x is true in the assignment, by definition of assignment.
Why is that in each clauses it's only one of the variables that is true?
Oh, there can be more variables true, like not x is true and not z is true in our example. But we select only one because this is our target.
Can we select only one and none of them?
Oh, that doesn't matter. We just have to prove that the answer is yes.
Oh,
yeah. So we are now proving this implication. Right? We're proving that if here the answer is yes, x is in A.
mm-hmm.
So the input here is yes. Then after the transformation, the input is still yes. And so we finish the proof. We can always do it. If here the answer is yes, we can consider an assignment that makes and so on and so on. Okay, fine.
One more time, why the true variables are not connected between themselves?
Okay, so here we will select in every clause a true literal.
Okay, only one.
Yeah, only one. But if we just take any true lit, we can never have that both X and not X is true in an assignment. And that means that here we will never select two nodes connected by a blue line. We will never select X and not X.
Yes, and the black line also can be.
Will not bother us because we select from each click at most
Only
one.
Yes, okay, I see.
We
So-
can even probably say that we can select any to literal.
Yeah, any true literal from the clause we select. Okay, so this is proven. This is okay. Now the third task is the other direction. I guess you already got it. Because you basically made all these remarks. Okay, let's go in the other direction. Imagine we have an independent set. Then we know that all these, so these k nodes, number of clauses nodes, it must be one node from each clause. Because we cannot have two nodes from the same click. So imagine independent set exists, then it must have a vertex from each click. Imagine that there is a click that does not have a vertex, then it means that some other click must have two vertices, but it's impossible because it's independent set. We cannot have two red things here in the same click because then they're connected. So this will not happen. It means from every click we select exactly one literal. Okay, now let us build satisfying assignment. So we assume an independent set exists. What is the satisfying assignment? Well, we set all the selected literals to true. If there are literals that do not appear in our selection, like the Y, it doesn't matter how we choose it. Say 0. Okay, and then I claim with this assignment, formula becomes 1. Why? It's easy. We selected a literal here, we set it to true. It means every clause has a true literal. Yeah.
We have a junction.
Yeah. So we have disjunctions, there is a true literal, and then each clause has a true literal, so it will evaluate to 1. So we have and 1 and 1 and 1 and so it's okay.
Can you repeat one more time why is every clause, each clause presented in the independent set?
So that's our construction. We look to the formula and we make a click for every clause.
So we have an answer on the independent set of size 3. Okay. the
Yeah.
number of clauses
Yeah,
is
3 clauses and yeah. Okay, and so why do we have a valid assignment? We might have a problem. What happens if one guy says x equals 1 and the other guy says not x equals 1? So this is something that will never happen because we have independent set. And if one click selects x and another click selects not x, it's not an independent set. We cannot have a red x and a red not x. And so we can always build the assignment. So this works. And so we have now proven that if answer here is yes, then answer here is yes. So we have proven this implication. And now we finished the proof. 1, 2, 3 steps. So that's how the grading goes, by the way. You present reduction and say it's polynomial time, and then you give the 2. So each time 1/3. And if the question is prove that blah blah is NP complete, then you have to say, oh, clearly problem B is problem B is an NP, and that's another point because blah blah is certificate. That's always the part you get for free. It's very easy for all these problems to prove they're an NP because they each time ask, does there exist blah 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 blah, and blah 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 is certificate. So, but there is this thing with like grading. If I know you, I know that you know this, but I need to pretend that every student is anonymous. So you still need to write. So there's the 4 things to check. Does he say that it's an NP because certificate is blah blah? It's kind of tradition, yeah. It's everywhere in the book, this extra repetition. Okay, so it's 4 things to check, like certificate, the reduction, and then it should be in polynomial time, and then the 2 directions. You can sometimes do the 2 directions in one time if you have at every step if and only ifs of your proof. Okay, but all these things are obvious, so let's not speak about it and go to the next one. So here we finished with this.
What's about the max cut problem?
It's for seminar.
Oh, okay.
Yeah. Let's now go from independent set to vertex cover. So do you remember vertex? It's really important problem, many applications. So vertex cover problem input is a graph. So the input is again the same input. Vertex cover. So you can just write VC because it's so common problem. So input is again DE and a number K. And the question, does there exist a set of nodes S of size K, so that for every edge, so every edge has at least one endpoint in the set S. Edge. Intersect S is at least one. So this is in mathematics written, but you understand. So you have to select a set of points, and every edge must touch one of these points. So let's do an example again. So does this graph have a vertex cover of size 2? Yes, who says yes? Yeah, so what's the vertex cover? And this, for example?
Yes.
No, this one is not covered.
We don't cover
Every edge or every?
Yeah, every edge. So for every, oh, sorry, I didn't write it clearly. So for every A and E. So an edge is a 2-element set, right? An undirected graph. So does the edge intersect S? So it must intersect S.
And we want which size? Size 2 or 3?
Size K.
No.
Yeah, here we want size 2.
Size 2.
Is it possible with size 2?
No, it's not possible.
No. Oh, size there is no like this. Yeah, no computer. Okay, now there is.
Are you sure that we should intersect him as the last?
Oh, sorry. Yeah. Yeah. I mean E and S. Okay. Every edge should intersect. So an edge is a 2-element set of vertices, and S is also a set of vertices, and so on. Okay, so this edge. So if we use these 2 nodes, this edge is not covered. So what do you think? Can we find 2-element set? No. So the reason is there are 6 edges and the maximum degree is 3. So the only hope is if we select 2 nodes of degree 3, but they share an edge.
But we
Yeah.
have an edge in the bottom, which isn't covered.
Yeah, if we select, yeah, that's the one. So, but we can say like, here are, this touches 3 edges, this touches 3 edges, but they, so there is hope because we have 6 edges in total, but the bad luck because 1 edge is shared. So the max we can get is to 5 edges with. Okay, this doesn't matter. You all understand the problem. Okay, how can we reduce independent set to vertex cover? It's very famous exercise.
suppose.
And so the observation is that so let us pick an independent set. Like this. This is an independent set. What can we say about the nodes not in the independent set? So here we have two nodes. And so what do you notice about them? They're disconnected. So take two nodes that are not in the vertex cover. Can they be connected? No.
No, we did this three nodes is in vertex cover, not in the.
Yeah. So this is vertex cover.
Yeah.
And now let's pick any two nodes that are not in the vertex cover. Can they be connected?
Oh.
What if they're connected?
There exists edge between them. That's not
Yeah,
in the
that's not
vertical.
covered. Yeah, so it's not real vertex cover. So any two nodes not in the vertex cover are disconnected. So what does it mean? Complement of vertex cover is independent set. Oh, by the way, I'm not checking Telegram. But nobody wrote something. Okay, so complement of vertex cover is independent set, and complement of independent set is vertex cover. And so reduction is very easy. We keep the graph and just replace k by number of nodes minus k. So if vertex cover exists of size k, then its complement is an independent set. So independent set of this size exists, and vice versa. If independent set exists of this size, its complement is vertex cover.
But in the task, we wanted to find the vertex cover size k and an independent set also size k.
No. Okay, this is different.
This is different.
If you want, I can use k tilde here to avoid confusion. Yeah.
Because in this case,
Yeah,
with
yeah.
an arrow, it's confusing.
Yeah, I agree. Okay. Yeah. So independent set of the vertex. So that was easy one. Okay. Now dominating set problem. So again, the input is a graph and some number. Question is, find the set of k vertices such that every vertex not in the set has a neighbor in the set. Okay, let me write it. Dominating set. The input. Yeah. And so this is nice construction because it doesn't exist a set. Okay. I should have and for every v then v minus s. I can write it faster. I can say that close neighborhood. Do you know this notation? Close neighborhood of S equals to V.
I missed something. How we found the other well, we showed the one side from independent set to vertex cover, and what about none?
Okay, let us first check that we understand what is vertex cover problem. Okay, so again, let me redraw the same graph. Sorry, dominating set problem. Let us check that we understand it. So this graph has a dominating set of size 2. So can we
Yes,
point at
it is.
2 nodes? Yeah,
It is left and bottom and the opposite of it. Yes,
Yeah.
but that's
that works. Okay, so every node is either in the set or it has a neighbor in the set. So that's dominating set. It's like from army. So if you have big front, you cannot defend every city, but you want to place armies so when you place the army, you need to go quickly to undefended city. Like it's in old days in Roman time, where the army they didn't have cars, and so they have to walk, and so they make sure there is an army in every city, and they, if attacked within one day, they need to go there, and then it.
Can you return on one step? Well, we showed about one direction from independent set to vertex cover, and what about the other direction?
Yeah. So we said if independent set exists, then its complement is vertex cover, and if vertex cover exists, its complement is independent set.
We use the complementation and
Yeah, we use it two times.
direction.
Yeah.
Okay.
Yeah. Okay. So, and now we need from vertex cover to a dominating set. And now it's not so easy. We need to modify graph, and we will insert gadgets. So we need to start from vertex cover. Okay, let's draw a simple graph. Of course, always I draw the same graph. And now the construction is as follows. We replace every edge, or we add a node to every edge to create a triangle. So basically, we turn edges to triangles by adding one node for every edge. So this will go to.
Can you repeat what's the
I will dominating set. So it's here. So do you know this N of S is the neighborhood of the set? That means the set and all its neighbors, it should be all nodes. In other words, every node should be either in the set or have a neighbor in the set. So here, every node, this node is not in the set, but it has a neighbor in the set. This node has neighbor in the set. That's dominating set. Yeah. So again, it's from the army. So if enemy attacks this city, then somebody can rescue in one day, can fight back in one day. Okay. So vertex cover and dominate. The construction is to just add a node to every edge. And now we have to prove the equivalence. Like this. And so we will have a vertex cover, we will have a number K, I forgot to draw. Yeah, and this will go. I think it's the same number K. Okay. So now I claim that if this has a vertex cover, then the same set is a dominating set. And then we will do it. So I will now do the forward direction as usual. And so is it clear? So we have a dominating set here. Then I claim exactly the same set here. No.
No, in vertex cover, from the left, we have vertex cover.
Sorry, yeah. And vertex cover has here also one. And so the vertex cover is dominating set.
Isn't nodes from vertex cover just the
the same node, the same answer here.
The same graph, isn't it?
No, the graph is not the same. So this has more nodes.
What if we don't change the graph?
Then the other direction fails. Yeah. So dominating set can be smaller than vertex cover. So you're right. Every vertex cover is a dominating set. I mean, assuming no isolated graph is connected. But other direction doesn't work. Well, yeah. So here we have the dominating set of size 2 and vertex. No, okay. Okay, so it's clear why vertex cover here is dominating set. Because we are okay for the black point because vertex cover is dominating set. We are also okay for the blue points because every edge has at least one endpoint in the vertex cover. Now other direction.
So, our solution may contain vertices that will add vertices.
Yeah.
So let's transform the solution to a solution that will work for the vertex cover. We can just try to move the vertex to the nearest.
Yeah, exactly. That's very good. So indeed. So okay, so we will make two observations. We might have general solution. For example, this might be a dominating set. I think so, right? Yes, that works. This is a dominating set, and our plan is to prove that every dominating set can be transformed to a dominating set only with black vertices. And then we will see that this will be a vertex cover. Okay, so let us imagine that there is a blue node that is in the dominating set. Imagine we move it to just any node here on the side. Look that this node only has two neighbors. It's not much. And moreover, these two neighbors are also the neighbors of this node. I mean, if we move this node, if we no longer make it in the dominating set, but we move it here, then this node also covers these two nodes. And of course, it covers itself. And so that's the plan. Let's just move it to any side. And then dominating set remains dominating set.
And what if we make the red vertex in one?
Even better. Then we decrease the size of our set. And so
like we need to say,
or we can just put it anywhere for the gray, because I said exactly equal to k. So then we merge it, we just put it anywhere we want.
How can we understand whether we need to move a node or node? Well,
We just, step one is get rid of the blue nodes in the dominating set.
how can we understand we have only a graph, not column. How can we understand it is a blue node or
No. We have an f of x. It means we got it by applying reduction. So we need to say that for every f of x where the answer is yes, the answer for original x is also yes. So we do have two colors. I mean, of course, and if you program it, there are no colors, but you can figure out. Well, no, we don't need to program anything. We just show that if it exists here, it exists there. Okay, now the other one we can also move to just any place, for example, here. And then we have a vertex cover here. Why do we have a vertex cover? Because all blue nodes need to be covered. So there are no blue nodes anymore in the dominating set, but every blue node has a neighbor in the dominating set. but there is a blue node for every edge. So the same set we found here is a vertex cover. And so we have proven backward direction now. And it's finished, so very good. And so it's a common feature. So one of the techniques to prove NP completeness is to go from one problem to another problem by building gadgets. Here we build kind of gadgets for every edge. Maybe we, in another problem, we transform the nodes to something more complicated, like in homework. Okay, but I shouldn't say that. And these gadgets, if they're a bit complicated, there is always such an argument, like we can always move this there and this will only increase, blah, blah, blah. And so, okay, so we have finished this. And so we are ready with this branch. Now we should explain this other branch. So it would be good if we get up to subset sum. That would be great, and it might be possible in 25 minutes. Okay, so I will remove this graph problem. And the next we will prove is we will go from tree set to not all equal tree set. What is not all equal tree set? So in tree set, we want every clause to contain a true literal. Not all equal tree set means that we may not have all three literals set to true. So it must be a satisfying assignment in which each clause contains a false literal. So in other words, for every clause, we cannot have 3 zeros and not have 3 ones or 2 ones, if it's shorter clause, or 1 1. Well, if there is a clause of length 1, then the answer is directly no, because we cannot have at least 1 0 and at least 1 1. So let me write it. What is this not all equal tree set? So the input is the same as 3CNF. Let me just fix the input. So here is tree set. Not all equal tree set. There exists an X, 0, 1, n, 5 of X. Okay. Every clause of 5, there is at least 1 true literal and at least 1 false literal. And note that this problem is symmetric in the sense that if we flip all variables of the assignment, we will still have a satisfying. It will still be a witness that the answer is yes, a certificate that the answer is yes. So we want an X such that every clause contains a 0 and a 1. If we flip the assignment, every clause will still contain a 0 and a 1. If we flip all the bits, it's kind of obvious. So yeah. And so if you want to prove some problem is NP complete and the witness is invariant under flipping, probably you might want to use not all equal tree sum. Okay. Well, this is the 2 problems with the same input. Now I will reduce tree set to not all equal tree set. I will do it with intermediate set through not all equal 4 set. So the plan is tree set reduces to not all equal 4 set, and this reduces to not all equal 3 set. So this is the same, but clauses can have length 4. And here length 3. Okay, so how to go from here to here? It could be an exercise. The clauses can be longer, but now, so what's the problem with tree set? There can be a clause. So we know that every clause contains at least 1 1.
Well, if we have all equal
To one,
signs,
yeah,
yes, we just add the n zero.
yeah,
the
yeah,
Zero and the
yeah. And how can we add the zero?
uh, let's use just another one.
Yeah.
Zero,
So
which is always
let's use this example there. We just create a new variable and we add it. And then,
fictional.
yeah, fictional variable. So let's think about this example there. So, and v is a new variable, and then the clauses are x or y, and v or x or z, and v or not x or not y. Not z. So this is very easy. And now let us see that's equivalent. And so there is the input. Why is it equivalent? First, if the answer is yes there, then we take the same assignment, set v to 0, then it's okay. Opposite, if we have satisfying assignment here, how do we know it's satisfying there?
Which direction is it?
Other direction. Imagine the answer here is yes.
So in every clause there is
Yeah.
a zero value.
Yeah,
Zero.
and a one value.
Uh,
How do we get the satisfying assignment there?
V is zero.
We can just throw away the zero and
If v is 0 in this assignment, then we can throw away and we are okay. What if v is 1?
we choose another variable and we rename the thing.
no, it's we don't need it because we know that it is not all equal and there must be a zero.
But they can be different in a clause.
No, so if v is 1, but then there is a clause with all zeros. If we throw away v, then this has only zeros. It's no longer true. So it's not a satisfying assignment.
So we try to throw away the x, the x.
No, no, no. We assume there is a satisfying assignment here,
Yes.
and we need to convince me there is a satisfying assignment there. And so we can go from here to there by throwing away the v.
Well, if we know that that's
By f of x, if you apply f of x to go from 3 SAT to NAE 4 SAT,
Yeah.
the v will be 0. So it will be 0. It won't be 1.
No, no, no. F of x just prevents a v in every clause.
Yes. Okay.
Yeah. Okay, maybe I should use a w here. It will be.
and also well, one more time, we know that not all equal for SAT is
Yeah, so here,
65.
yeah. And
And,
there are two cases, if v equals 0, and then we are done, because we can just use the same assignment.
And
But what if v equals 1? Yeah.
well, we can't go away because
No, we have to throw away v. The value v equals 1, we throw away anyway, because we don't need it for the assignment here.
why? Our clause will be false. And we have a conjunction.
Yeah, but the question is, if you know that this is true, this satisfies not all equal condition, then we have a satisfying assignment here. And so tell me, what is the satisfying assignment? And we need two cases. And the first case, v0, we know, v1, we don't know yet. Okay, I will, yeah.
Then we know that in all models we have 0, so when we throw v and convert all letters.
Yeah. Yeah.
one into
Okay. Oh, sorry, you told already before this.
No,
Okay,
just-
yeah.
no.
Yeah, sorry, okay, yeah. So basically, what are you doing? So how do you get this assignment? You need to
Flip all this.
flip all bits, yes. And then
Oh, okay, we're again using the property about.
by symmetry, yes. So we flip all bits, then V is 0, and we do the same. Okay. Yes. So
Would you just try to
okay, there was a confusing discussion. And so now we want to prove this inclusion. And so we have to check two things.
Yeah.
So if we have a satisfying assignment here, we set V to 0 here, and we get one in which every clause, blah, blah, blah.
Yeah, okay.
The hard part is, well, not so hard, the other side. Now let's do this direction. Imagine that here we have satisfying assignment. How do we find satisfying assignment there? Well, there are two cases. In the assignment here, V is 0.
Yeah.
Then we are done. We use the same values for X, Y, Z. Because every clause contains 1. If V is 1, then we flip all values of X, Y, Z, and then we are good there. Why? Because V is 0 now. We flip all the values of P, X, Y, Z,
Okay.
and then we are in the previous case. And this is because the not all equal condition is symmetric under flipping. Okay. So this one is good. Now the second one, we need to go from not all equal 4 set to not all equal 3 set. And this we apply idea of resolution. It also works for this condition. So let me tell how it goes. So we have a clause, every clause with 4 variables. W. So it's just 4 variables. We will split into 2 clauses. So this reduction goes like this. Y and A. Okay, I don't have negation, but it doesn't matter. Not A and C and W. And I claim that even a satisfying, if this is part of satisfying assignment, not all equal assignment, then we can choose a value of A, 0 or 1, so that these two things are also satisfied, and vice versa. So why is it true? So imagine we have a satisfying assignment and there is a 0 and a 1 here. For example, Z is 0, W is 1. Then we have a 0 and a 1 here.
Then we can choose A,
Yeah, whatever we want.
whatever we want.
Opposite of Y, for example. And then the same if 0 and 1 are this. So the next case is that the 0 is on one side, 1 is on the other side. So we have 0 here and we have 1 here.
Well,
But then
we again can.
yeah, we choose A opposite of X, and then not A will be opposite of W. And so this one is easy.
And why we should keep the opposite of W? We know.
So in both clauses there must be a 0 and a 1.
Oh, not only. Okay.
Yeah, not all equal 3 set. So we go from here. We just make the clauses shorter, but we double the number of clauses in the worst case. Okay, and that means this is okay. I need to explain the other direction stuff. So imagine that this is a not all equal assignment. But it means we have a 0 and a 1 here. This is a case where we can do the negation. Imagine that the assignment here is false.
Can you please repeat the first side?
Yeah.
So we take the 0 value and the 1
value,
and we construct.
and we choose A
For
according.
each other variable. Then,
Yeah. In all cases, we can find A. So yeah, we look at 0 and 1 variable. And if they're in the same clause, it's easy because we can just focus on the other. And if they're in the different clauses, it's also easy. Okay. And now let's assume that this the assignment makes this clause false. then there is no way to choose A so that this becomes true. Okay, what does it mean? This clause is false. It means that it's either all zeros or all ones. But if it's all zeros, then we have this situation. So regardless of what we choose A, one of the two will be all zeros. So there is local transformation. If this has a problem, then this has a problem. If this works, then this works. And so that's the proof that is. So we basically use the same assignment. Just the inserted dummy variables, we need to deal with that. But it's easy.
Can you repeat again the other direction? The last one.
Yeah, okay. So imagine we have a reduced problem
Okay.
that sorry. Imagine that the answer is negative in the original problem.
Okay.
Then I claim the answer is negative in the reduced problem.
Well, each of them
It
are,
means, yeah, let me
are
say,
equal.
yeah, for every assignment, we have a problem. Let's look to the clause with the problem. And so sorry.
The problem is in every clause.
Yeah, yeah.
Oh, no. There is at least one clause with the problem. We look at the clause with the problem. There are only zeros in that clause, and
yeah, okay. What I'm saying is for every assignment of original variables and dummy variables, let's look to the original clause. So let's ignore the dummy variables and look to the original variables. In the original clause, if we apply it, we will find the problem. And then whatever assignment we choose, we have chosen for the dummy variables, there must be a problem. So that's the structure.
yes,
It's extra back and forth. So that's the disadvantage of using this
we
negative
shall
information.
have a problem because
Yeah.
we have all zeros except the dark variable, and dark variable can be one in one clause and zero in another, and we need it to be one in every. So
Yeah.
it's the problem.
Yeah, so for every clause here, if there is okay, so we have proven this reduction. And there's 10 minutes left. 1, 2, 3. Okay. So from not all equal set, we can go to tree colorability. And there I need to draw some gadget. Okay, so now okay, in not all equal tree set, we can assume all clauses have exactly length 3. So let us think why it is. First, clauses of length 1. If there is a clause of length 1, we immediately know the answer is no. So it's easy to make reductions for such cases. I will not talk about it.
If we have length 2, we just need to
Yeah. But what means a clause of length 2? Imagine that we have a clause X or not Y. And exactly one variable needs to be true and one needs to be false. There is only one way to satisfy it is if X equals Y. So that means we can get rid of all clauses of length 2 by renaming the variables.
Well, but what if we have a clause X Y?
Yeah, okay.
Not negation Y, but just
Yeah, if there is no negation,
Then-
then every appearance from Y would be replaced by negation of X.
they just open.
Yeah, just so this
So
is
we are using order or opposite or
Yeah.
the same. Okay.
yeah. So in not all equal tree set, all clauses, we assume it has length exactly 3. Okay, now let's build the gadget. So there are gadgets for clauses, for variables, and one special node. So, okay, the tree colorability problem. So do you remember what it means? So we are given a graph. And the question is, can we color all the nodes with red, green, or blue? Let me write it. So that no edge connects 2 nodes of the same color. So the input is a graph. Then can you color all nodes with RGB? That's just the color of my markers. And such that every edge connects nodes of different color. So this graph is tree colorable. It's very easy. Actually, you might want to look to Brook theorem. So if the degree is at most number of colors, you're always good. So this one is tree colorable, but a clique of size 4 is not tree colorable. Okay.
And there is a criteria of tree color.
Well, if the degree is small, like if all degrees are at most 3, then the graph is tree colorable, except okay, some cycle of odd. Okay,
So
expect
just,
a clique.
personal
Yeah,
case, yes.
yeah. If the graph does not contain a clique of size k, then every and it's not a cycle, then every graph with max degree k is k colorable. There is kind of obvious, if the max degree is k minus 1, you can always color the nodes because you can, the greedy algorithm works.
Okay.
There are k minus 1 neighbors, so you always have one color left to color it in greedy way. Okay, but let's not speak too much about this because we need to. So now we start with the not all equal tree set formula, and we just said that all clauses can be assumed to have length 3. So let us add something, not y, something like this, or that's an all positive one. Otherwise, it's trivial. Okay, let's assume that this is not all equal 3 set, and now we need an input for 3 color. And so our graph will have a triangle for every clause, and every node is labeled by the literal as usual. So for the first one, we have not xy. And then for all the variables, we will make the gadget will be just a line. So x, not x, y, not y, z, not z. And only that's one.
It looks like a matching.
Yeah, the matching. We are not yet ready. We still need to make interconnections. So the second clause x is y. Okay, I will not draw the third because it's clear how to do it. And now we connect. So here is variable gadgets. We connect them to the closed gadgets using opposite literal. So x, not x goes to x, not z goes to z, y goes to not y. And the same here, z goes to not z, y goes to not y. And then there is one special node. I will draw it blue. So, and this is connected to all the nodes in the variable gadgets. So you see that there are 2 colors left, and so we have 2 orientations to define true and false. Okay, so now the construction is finished. So if we have a clause, then we know how to build this graph. So the size of the graph is linear in the number of literals. So number of nodes of the graph is linear in the number of literals, and all degrees are bounded by, no, the variables can have large degree, but number of edges is basically number of proportional to number of literals. We can just simple construction, we can build it in polar angle time. Okay, now let us look as usual at the forward direction and say, assume that has a not all equal tree set assignment. So all clauses contain a true and a false literal. How will we color it? Well, we will make green all the literals that are true. For example, not all equal assignment here is z equal 1 and x and y equal 0. Does it work? Yeah, it works. Z equals, no, it doesn't work. Y needs to be 1. That works, right? Okay, so all three true literals we will make green. So not x, y, and z. This one, y, is green. And all the others, okay. So the variable gadget, we set the true literals to green, the other ones to red. And here we try to do the same. I need to be careful because we cannot have 2 greens or 2 reds in the same triangle. But we know every triangle contains a false and a true literal. So we are out of problems. And for the third variable, we can use the blue color. And so we've built the coloring. Why can we do it? Because no two literals are always connected to opposite literals in this graph. So we have no problems when we go from variable gadgets to closed gadgets, because in this connection, we always use opposite literals. This one is connected to all blue. So in these connections, in these blue connections, also everything okay. And inside the triangle, we use 3 colors. So everything is okay. So set not all equal assignment here gives not all coloring here.
And what the blue nodes in the left?
That's just a special note, and just to avoid using blue color in the variable gadgets. Okay, now the other direction. Imagine this graph has a coloring. How do we retrieve the satisfying assignment? Well, we read it off from the variable gadgets. And so now we see that in every clause there must be a true and a false variable literal.
Well, in every clause we have 3 color, and we know that 2 of them is just opposite.
Yeah. So we so if you have coloring, then the green one. Okay, we can always rename the coloring that this one is blue, and that the true literals are green, and the bad one, the red. False ones are blue, and then we just look to the neighbors or just by construction. We use the property that in these connections we only go from literals to the opposite ones, and so x is equal to e. Okay.
Can you repeat again? How do we color blue?
So we assume that coloring exists, and we want to find not all equal assignment. Okay, that's our task. First, we rename the color so that this one is blue.
Okay.
Okay, then we know that here we have green and red. And we say that the green ones are true literals, the red ones are false literals. It doesn't matter, this assignment is symmetric anyway. And then from here, we read off that indeed every clause contains a true and a false literal. Because if there are two true literals, that means here we are next, 2 times next to a green one. And so 2 times we need to use, sorry, what I'm saying is if we have 3 true literals, then we cannot color it because 3 times we are next to a green one. Yeah, it's kind of
why not that not Z is blue and also the dot
yeah, because this is a triangle.
it's not connected to the dot in the left. Yeah, it's not connected.
Yeah, so we must use the blue one. But the blue one is always safe for the connections.
okay.
Yeah, we can ignore it. But for the red one must be next to a green one in the variable gadget. Okay. So yeah, so there are 2 more things that are kind of important. So, but I will stop here because otherwise I'm talking too long and you get tired. So I will explain it in 2 weeks how to do this kind of nice steps. Or maybe next week if you're fast, I don't know. So this we have done. And so let us have a break and then in 10 minutes at 9:45, it's seminar. So then Nikita will be. Okay. So I will stop streaming.